Limits of rational functions. We have already seen that if from numbers 13 through 22, it was easy to determine the limits as x goes to infinity or negative infinity from numbers 13 through 19, because as long as the numerator's degree is equal to the denominator, then you just take the coefficients, the ratio of the coefficients of the leading terms for these cases, and of course, okay, these cases, where else? Also number 18, see they have the same denominator. And then if the numerator's degree is less than the denominator, then the limits are 0. Right there. Okay, so now let's look at numbers 20, 21, and 22. But I will just work on numbers 20 and 22 in the next slide. Let's go ahead and work this out. The difference between 20 through 22 is that, among the other problems there, is that the degree of the numerator is greater than the degree of the denominator. The g of x, we know that this function has an oblique asymptote. But right now, what we're concerned is, what is the end behavior? In other words, where does the graph go when x heads off to plus infinity or negative infinity? And what we want to do here is to divide both the numerator and the denominator by the leading coefficient, the power of the degree of the leading coefficient of the denominator. Dividing each term by x squared is the same as multiplying both the numerator and the denominator by 1 over x squared. And what we get will be, okay, g of x becomes, you see that x cubed is divided by x squared, so you're just left with x. 7x squared divided by x squared is 7 minus 2 over x squared. Whole thing will be divided by, of course, that becomes, when you divide this by x squared, it becomes 1 minus 1 over x plus 1 over x squared. And now we look at the end behavior. In other words, what happens when x approaches plus or minus infinity? And we know that if it's 1 over x to a power, it always goes to 0. This goes to 0, it goes to 0. And what's left is just an x plus 7 term. However, x will dominate 7 when x goes to infinity. So the limit now of g of x as x approaches infinity will depend on x. And as x goes to infinity, of course, x will go to infinity. It's just the identity. And of course, the limit of g of x, when now x heads to negative infinity, will follow what the x does. So it's negative infinity. Now let's look at number 22. Divide both the numerator and the denominator by the highest degree that occurs in the denominators, which is x to the 5th. And what I'll do is I'll go ahead and write this now as h of x is 5x cubed minus 2. That's x cubed divided by x to the 5th becomes 2 over x squared plus 9 over x to the 5th. The whole thing will be divided by, okay, I will rearrange these terms. Let's go ahead and rearrange these terms. That way this comes out as the leading term. So you're going to get a negative 4 and then a plus 1 over x to the 4th when x is divided by x to the 5th. And then plus 3 over x to the 5th. And as we have done in number 20, this goes to 0, that goes to 0, this goes to 0, that goes to 0. So we are left with 5x cubed, which is divided by a constant that's negative 4, which means it will affect the sign of 5x cubed. So if we take now the limit of h as x approaches infinity, we see that the whole thing will approach negative infinity because of the sign of -4 affecting the dominant term 5x cubed. So this is minus infinity. And when we take the limit of h as x approaches negative infinity, that x cubed, when you raise it to that x that's going to negative infinity, when you raise it to a cube, then it will become minus infinity but then you're dividing by a negative constant, so this is now plus infinity. Infinite limits. Find the limits in exercises 37 to 48 depending on what they ask for where the x goes. So let's just say, let's go ahead and work on number 38. We are letting x approach 0 coming from the left. So this 5 and this 2 remains there, so it's 5 over 2. Now again, we're looking at what happens to x when you let x approach 0 coming from the left. That means it gets close to 0 in the negative sense. So when you have a number divided by a very, very small number that's approaching 0 negatively, then the whole ratio would go to negative infinity. Okay, what about number 40? Let's do number 40. Okay, you're looking at 1 over x minus 3, and you're approaching 3 coming from the right. So when you're coming from the right, think of the values of 3 like 3.1, 3.01, 3.001, and what do you get there? If you have that case, then that means this number that you get close to 3 is greater than 3 by just 0.01, 0.001, etc. So the whole ratio now would be positive infinity, and so on and so forth. So you do the same thing with number 42. Why don't we do number 42? Just because it looks interesting. Okay, we are approaching 5, -5 from the left side. So if we are approaching -5 from the left side, which of these two would be, what would be the sum of 2x and 10 when, say, you try to plug in -5.1, -5.01, etc. This number would be less than -10. So the whole expression would have, okay, 3 times, it's very close to -5, so it's still negative. 3 times a negative number is negative. Now this, when we take the sum of 2 times, say, 5.1, -5.1 plus 10, this is going close to 0 in a negative sense. So now you have a negative over 0 in a negative sense, means it will approach plus infinity. Okay, now let's look at 44. In number 44, well, we have a fixed sign on the top, and then what happens to 0 as you approach 0 from the right or from the left? Well, it's not really going to affect it. This will always be positive. So what we'll have in number 44 is that you have a -1 divided by 0 will always be positive, close to positive 0. And then you have 0 plus 1, that's just positive. So all in all, what you have is a negative divided by a number that's very close to 0 positively. Then the whole expression will approach negative infinity.